this is going to be like a very brief introduction to OpenACC, kind of a case study of how you can easily port your application and run it with OpenACC. And there was an interesting question at the end of the previous talk about the kind of automatic data movement between CPU and GPU, between CPU and accelerators. And it just happened that I have a kind of a new slide deck that I just prepared that actually touches this topic specifically. So, so we'll see. What's OpenACC? So this is another, I guess you had the whole day on OpenMP. So OpenACC is another open standard for the directives for accelerators. It was designed specifically to target accelerators. It's simple, and I'll show you in a bit how simple it is. It's open, so anyone can implement their own kind of compiler or the way to follow the standard. And it can work on AMD, Intel, NVIDIA GPUs. And it's also portable. And we also try, so I think the key point here is that it's also performance portable. So sometimes you implement your code using directives, but it works on one architecture, but it completely fails on the other architecture. And so the hope with OpenACC is that it can actually be, have reasonable performance on multiple architectures. So there are a lot of members, as you can see here, in the OpenACC committee. And I'll just skip through that. And yeah, just deep dive into the case study of how you can port this application, some application to OpenACC. And so the methodology that I will use is the standard one that I think if any of you have been to our GTC talks or webinars. So first, when you have your program, you need to identify the parallelism, right? So maybe you don't know where you can actually use accelerators for your code. So the first step is always try to find the portions of your code where you can port it to the accelerators using the directives. And there are tools available for that. You can use them. And once you found the necessary portions, necessary functions that you want to port to the GPU, you want to parallelize them with OpenACC. And so this is the big step that I'll focus on today. And then what you usually do next is you try to optimize your code. And there are two things here. So you want to optimize the data locality. So you want to keep, the data close to the GPU, while you're doing something on the GPU to avoid frequent data transfers between CPU and GPU. And there is also, improvements in the loop performance that you can do. And there are many things you can achieve with OpenACC on that. And I'll just briefly cover this kind of advanced parts on the optimization and mostly focus on the parallelization of the loops with OpenACC. So the case study we're going to look today is pretty simple, although still may be relevant to some fields. So we're going to look at just a simple JACOBI iteration. You have a structure grid, and essentially you perform a stencil of like 4 points in 2D, and you assign the next value as an average of the 4 points that are across this center point. So, it can be, probably not this particular implementation, but something very similar can be found in many, CFD codes and explicit schemes. Let's look at the code. So I'm just kind of showing up this is a simple, first, the while loop. I think I have some animation here. So first, we just go over the while loop. So the first is just the iteration loop, right? So we just do a bunch of iterations one by one. And then in each iteration, we compute go over all the cells and then compute the average in this first kind of double-nested loop. We calculate the new value, just averaging all the values on the neighbors. Then we compute the error, the maximum error. And so we're going to use this error to see, when we need to stop our loop, right? So once we converge, we don't need to do any other iterations. So we are going to do a maximum of all the cells in our computation, right? So you can see here we do the maximum, and then we compute the maximum across all the cells. And then there is another part here where we actually just swap the input and output arrays. And here, so it's obviously there is a more efficient way to do that, right? So you can just swap the pointers. But just for educational purposes, we show, OK, in this case, we're going to just assign it. It may be something more, some more complicated situation in your real code, for example. But this is kind of the program that we're going to port to use OpenACC directives to make it run on the GPUs. OK, so the first step is how we can identify the parallelism there. And there are many different tools available. I mean, you can choose whatever tool you want. I'll mention a few of them. Yeah, so there's Vampire, pgprof, gprof, and usually, if you're familiar with some particular tool, then use it and identify the parallelism. I'll show an example how you can use pgprof. It's a tool provided by the PGI compiler. And so what we do here, we first, we have our program in C. We just compile it with pgcc, and we provide two options here. So minfo all will show all the information that the compiler can generate for, whether it found any parallelism or whether it, generated some kernels or anything. So usually I would recommend to use this option all the time because it's very useful, and we'll see that in later slides as well, why it's useful. And this option simply embeds the profiling information into the executable so that later on we can use it with pgprof. Then there are a couple other steps. So you use pgcollect and then pgprof. And what you'll see in the end is, it's probably hard to see, but essentially it will show you some hotspots. OK, this is, this double nested loop that we have here is the hotspot in our application, so probably want to port it to GPU. Of course, in this simple program, you probably can figure it out on your own. But if you have a more complicated program, right, and you struggle to find where I can spend most of my time, right, so this can be a useful tool to use. So it will also actually, so the pgprof tell you some information about the number of kind of calculations per load store instructions. So the average thing that you can also compute it yourself, but you can use this tool as well to do that. And it will hint you, OK, you might want to use, for example, OpenACC or CUDA to port these loops.
Excuse me.
Yep.
All right. The computational intensity. Did you say is that calculation instructions or are they actual bytes and operations?
I think it's instructions, but I'm not 100% sure. So we can check that in the documentation. Yeah. Let's assume we found where we need to, where is the parallelism. So here, I mean, you can use the pgprof or our other tool to find the hotspots, right? But it's generally, so you still need to do some work to figure out, OK, this is the parallel loop, this is not the parallel loop. This is something that I can parallelize, this is I cannot parallelize maybe. So there is some work that is necessary to figure this out. The compiler cannot do this automatically for all the programs. It can figure out for some things, but not for all things. And so what we need to do first, OK, in our program, we know, OK, the outer loop iteration, right, it's not parallel, right, because we simply do this iteration one by one. All the results depend on the previous results, so we cannot parallelize the outer loop. Now, these two loops are actually completely independent. All the iterations are independent, so we can parallelize them. And we know that we can parallelize them, so that's good. We identified the spots that we want to port to the GPU, to the accelerator. Now, once we found, OK, this is the parts that we need to move to the GPU and run on the GPU, how we can use OpenACC with that to port it. So the syntax for OpenACC directives is very simple. It's kind of similar to OpenMP, but instead you need to provide pragma ACC. And then there are a lot of directives you can specify, and I'll cover some of them. And then usually there follows a structure block that you can, that will be parallelized. And similarly for Fortran, there is the same like start and end directive. So the first directive that I want to tell you about, the OpenACC directive that I want to tell you about, is kernels. So this is a very simple one, and all you need to do is just put pragma kernels, pragma ACC kernels, and then you have some code, and the compiler will try to figure out, okay, whether I have any parallelism there, can I create some kernels from that code, can I move it to the GPU, so it will do everything for you. So in this particular case, for example, we have two loops. The compiler will figure out, okay, this is like the completely independent loop, so I can actually create a kernel for that. And the second loop is also completely independent. I can create a second kernel for that. So the kernel is if you don't know, this is a parallel kind of function that we execute on the GPU. So this is a very simple construct, right? So you just specify pragma ACC kernels and then hope that the compiler will figure it out. Now, let's try to do this in our code, right? So let's try to put the pragma ACC, and we know that these loops should be parallel, right? The other loops should not be parallel, so we don't want to put the pragma ACC kernels out of the outer loop, so we still need to do some manual work. So we still need to figure out, okay, maybe we just need to put it here. And then essentially, so it will tell the compiler, okay, look for the parallelism in this region, try to move it to the GPU, run it on the GPU if possible. Okay, so that's simple. Now, if we compile that, and this is like the compiler output, which is very useful to understand what happened. And I'll first go through the some options here. So ACC provides that, just use accelerators, and TA is a target architecture, so use Tesla, which is, I think stands for the NVIDIA GPUs. And then we still use the minfo to provide all the output of the compiler, and then just specify the file. So the output is actually very interesting, and we'll focus on a few things here. So you can see it tells us that, there is some dependency, which we'll go over in a bit. But the main thing to understand here is that it actually created some kernels. So you can see there is an accelerated kernel generated. Then there is a reduction kernel generated for the error that we're doing the reduction on. And then there is also another kernel generated for that. So we know that compiler did some, found some parallelism there. Maybe not all the parallelism that it could, but it created some kernels and did some initial creation of the code. So now, what are the problems here, right? So before we actually run this code, it's useful to look at the compiler output and see, okay, what happened, what was wrong, what happened wrong maybe. So in this particular case, we can see that the compiler told us, okay, there is some accelerator restriction because the size of the GPU copy of A new and A is unknown. So we specified the kernels, but the compiler couldn't figure out, okay, how much data I need to copy to the GPU, right? And then it told us, I cannot accelerate it because I don't know how much data I need to copy. Very easy trick to fix that. So of course you can do the data directives, and I'll cover them in a bit. But in OpenACC, and specifically in the PGI compiler, you can provide this option called TA Tesla then managed. So what this option does is it simply offloads all the data management to the CUDA driver. So you no longer need to figure out, okay, I need to move the data to the GPU close to the GPU, or I need to move the data back, and when I need to keep the data on the GPU, or when I can copy it back. If you simply specify that, the OpenACC will use CUDA driver and unified memory functionality that we have. So what will happen, so this is a simple example here. So we allocate some data on the CPU using malloc. And then we have some loop that initializes the data on the CPU. And then we have some other loop that we want to port to the GPU, right? And we specify the kernels around that. And then we, again, access the data from the CPU to do something. So if we just compile that with Tesla managed, this will be allocated on the CPU and filled out on the CPU. Then in this portion, we don't need to insert any particular data directives or hints to the compiler how much data we need to move or what's the size of the array or what. You don't need to do anything all that. You just can specify the managed option and it will figure it out on your own. And if we look at the output now, so we can see that the acceleration restriction lines that we had there, they're actually gone, so we don't have any more of them. We actually still have some dependencies. So that means that we still need to look into that and see what's going on there. But at least now the compiler, it figured out, OK, I don't have any restriction for the accelerator, so I can actually run this code on the GPU. You can run this code. It will run. It will not run as efficiently and because of the loop dependencies. But it's already kind of a simple way to run the program. And then if we just look at these dependencies, so what happened here is that on the left side, you can actually see all the lines in your code. So you can see, OK, this loop, for example, it had some dependencies, and it couldn't parallelize it. But the other loop was parallelizable. So the inner loop, so we had this double nested loop. In the inner loop was parallelizable, but the outer loop was not parallelizable because compiler just couldn't figure it out. Sometimes compiler can figure it by using some pointer aliasing, for example, if you use restrict pointers or some particular access pattern, it can figure. Sometimes it just cannot. So in that case, we have a special clause for that. But before I go to the special clause, I want to introduce another directive that is similar to kernels. But instead, so in the kernels, you just specify, OK, here's the scope, and try to find parallelism in all the kernels there, right? There is also a parallel loop, and they actually use together the parallel and loop. And so the parallel loop directive, it specifies, OK, this is the loop, and just find, this would be the kernel. So create the kernel for this loop. You can also use the ACC loop on some other nested loops, like the inner loops and that, if you want. But essentially, the parallel loop creates a single kernel. And so this is alternative for the previous approach, because you can, in the previous case, you kind of rely on the compiler to figure out where all the parallel loops. And in this case, you specifically tell, OK, this is the parallel loop. I know that. So please do the kernel for that. And then there is the independent clause. So this is what will help us with our problem. So sometimes compiler, if you use kernels, especially, can figure out, OK, this is actually the parallel loop. What we can do is we can provide, OK, pragma ACC independent. In that case, it tells us, yeah, this is the independent loop. So yeah, so the compiler will know, OK, I can safely create the kernel for that. So you kind of provide a guarantee for the compiler, OK, this is the parallel loop, and I know that, so please create the kernel for that. So here's our slightly modified program, right? So we used kernels. We also specified the pragma ACC independent. Let's look at the performance and what we have in the output, right? So I'll just go through that. So we told the compiler these loops are safe to parallelize, so please parallelize them. So what happened now, we can see that all the restrictions or all the warnings, everything about the loop dependencies is they're completely gone. So we don't have anything like that. So we have two nice words. A loop is parallelizable. So the outer loop and the inner loop are parallelizable. And then the second set of loops that we had for the copy of A new and A are also parallelizable. When you get to this point and you don't see any restrictions or any dependencies or anything, usually means you're in a good spot, so you don't need to do anything else. I mean, just run your code and you would get a reasonable performance. And in fact, if we look at the performance, so this is a chart for this particular problem. So we used OpenMP actually for CPU. And we used OpenACC, the code that I showed you previously, and we run it with Kepler GPU. And this is the performance we get. So we got almost, I think, 6 point something, like 6 to 7x speed up over the single socket on the CPU. So you get really good performance. You don't really need to do almost anything, just a few things, add kernels directives, right? And then maybe if you can figure out, okay, these loops are parallel, just put the independent there, and that's it. You don't need to handle the data movements. You can do that, and it's actually recommended. So once you do that, once you went through this approach, you can start thinking, okay, maybe I need the data here and here, so maybe I can use data directives and actually figure out where I need to put the data. And so kind of the next set of steps for you is to try to expose some data locality right through the manual data directives, and I'll show you in a bit. And then also try to optimize the loop performance. When you got to this point that you're faster than CPU, or maybe you still want to optimize your code, there are lots of tools you can use, and I probably can do another presentation on that, like a few hours. But just briefly mention that there is a very useful tool called Visual Profiler. So it works with OpenACC, with CUDA, with anything that runs on the GPU. So it will tell you, you can see the timeline of what's going on. So where are the data copies? So for example, on this slide, here we can see this is a data copy, this is another data copy, this is a kernel. So you can actually see what happened with your application. Especially this is useful for OpenACC because if you had something like that, like I showed you before, you didn't know, okay, where was the data movement because I didn't specify that. So it's useful to look at the Visual Profiler plot and see what happened. Now, if you want, if you found that, yeah, the data movement was not efficient, maybe I want to do it manually and I want to handle it on my own. We do provide, I think, similar directives that are existing in OpenMP as well, like OpenMP4. Is you have the OpenACC data and OpenACC data enter and exit. So the OpenACC data is just for the explicit data region for the particular scope. I want to copy in the data, copy out the data if I want. Then the unstructured regions is where you want to do something and then maybe do something, do the copy in one function, then do the copy out in another function. And this is useful for like C++ classes, for example. If you have a constructor and destructor, you can do that. And there are a bunch of other things you can do with data locality. I just kind of covered a few things. And then if you want to optimize further performance of your loops, there is also a fine-grained control that is exposed in OpenACC. I won't go into details, but I want to mention, so you can actually specify for each loop whether you want this loop to be executed as a gang, worker, or vector. And so the gang, if you're familiar with CUDA, this is a thread block. I believe it's also in OpenMP4, it's a team. I think it's something like that. So the vector is kind of the simple unit, and it's also each worker executes a vector. You have kind of this 2D hierarchy, right? So you have vectors. And they are assembled into workers. And then you can specify, okay, I want to have this inner loop executed as a vector. And then this outer loop, I want to execute it as a gang. So essentially, this will be one gang, I0, right? I1 will be another gang, and so forth. So this is kind of a fine-level control if you understand the architecture and you want to expose kind of more. And if we actually go back and look at the compiler output, we'll see that it generated, a gang for the outer loop and the vector for the inner loop. So you don't have to do that, but if you know more about your code and know, okay, in this particular inner loop, I only may have like 4 iterations, right? So I don't want the compiler to create a vector of 128. I want the compiler to create a vector of 4, right? So I want to specify that. So these are kind of things you can look into and start, optimizing your code with that. So try to identify the parallelism, then port it to OpenACC, right? You can parallelize the loops, try to express as much parallelism as possible, and as soon as you get correct results and running on the GPU, so that's a good point, right, to stop, and then you can continue optimizing with the, explicit data regions, right, and trying to optimize for data locality, or you can also optimize the loop performance as well. and I'll just stop here. This is pretty much all the same links that I showed in my first talk, but these are still useful for OpenACC as well. Okay. Any questions? Yeah.
So how does this interact with OpenMP? So if you have like 4 threads running something in OpenMP that runs into one of these directives, what would happen?
Yeah, I don't know how it would work with OpenMP actually. So we should look into that. I've never used it with OpenMP. Like,
Can it separate? Does it have the functionality of OpenMP, like parallel for loop?
yeah, I should.
Yeah, but not on the GPU, like on threads on the CPU.
Yeah, I mean you can compile this for the CPU architecture and just run it on the CPU. So you can just execute the same parallel loops and just run it on the CPU. It will work. Yeah. If you have a compiler that compiles OpenACC for CPU.
So if I'm an application scientist and I have a GPU, can you just compare for me CUDA and OpenACC? How do I choose which one?
Yeah, sure. So and I think I had an exact slide on that in my first talk. Like we have libraries, directives, and languages. We can talk CUDA, for example. So if you want some low-level details to the architecture and want to, optimize it as much as possible, you would probably need to use CUDA. Directives are useful to get started with, and I mean, I think the ideal code should have most of the, bulk of the code should be ported with directives, and only a few functions that are really performance, intensive and that are really critical for your performance. Maybe you should port them to, using CUDA. And you can use OpenACC and CUDA and libraries in the same code. There is no problem with that.
If there is a function call within the loop,
Yep.
then how will it behave?
Yeah, so there is a special directive called routine. So you can specify a function as a routine, and you can also specify, okay, this is a vector routine, or this is a gang routine, or this is a sequential routine. And so, yeah, so there is a special directive for that.